Let me get rid of this chair too while we're going at it.
So we're happy to have Justin Hilburn to come visiting us and give us a talk about two categories of linear symmetry.
Thank you for inviting me. I'm really happy to be here. So this is something that I started drawing pretty much at the beginning of all my talks these days. Elliot, who's in the audience, has started calling this the mirror symmetry. You can think of this as being like the trunk. And basically this is like something that sort of organizes 3D mirror symmetry, which is like a particular duality of 3D n equals 4 supersymmetric gauge theories, and its relationships to like other areas of math and physics. And so there's two sort of kinds of relationships that are like going on in this picture. So the first ones are these ones that I've drawn as like an inclusion and like with this boundary, and these things are like boundary bulk relationships. And so what that means is that it is possible to study supersymmetric configurations where you have some sort of a 4 manifold with like a 3-dimensional boundary where you have 4D n equals 4 super Yang-Mills on the bulk and this 3D n equals 4 on the boundary. And roughly the reason it's possible to do this is that this thing has 16 supercharges and this thing has 8. Or you can actually write down an embedding of the supersymmetry algebra. But generally, like the best you can do is half the supersymmetry on the boundary. And similarly, in this 4D n equals 4 theories, they're the ones that control like geometric Langlands. So like this is like a very like important like theory like in mathematics and physics. So that tells you already that there's going to be some sort of a relationship between 3D n equals 4 theories and hence 3D mirror symmetry and geometric Langlands. And then the other one that's really, really nice is there are these 2D n equals 2 comma 2 theories. So these things have 4 supercharges, which is half of 8. So these things can be supersymmetric boundary conditions for this. And this is like where ordinary like mirror symmetry lives, like the homological mirror symmetry of like Kontsevich, and the Fukaya category and coherent sheaves. And like the nice thing about like all of the theories that one sees like living along like the trunk of this mirror symmetry is that they all have, this 2D theory has like the famous A model and the B model, which are topological twists. And once you've chosen, embeddings of supersymmetry algebras, this thing just induces like A and B twists all the way up the chain. So like basically this thing has a 2D A model and a 2D B model. This has a 3D A model, and a 3D B model. This one has a 4D A model and a 4D B model. So in this case, it's like these are both Kapustin-Witten twists. I think at 1 and I. And then the B twist here is the Rozansky-Witten theory, and the A twist is like 3D Seiberg-Witten theory. And these things are all compatible in this bulk boundary system. So that means that like what you sort of learn from all this and what we'll see like in this talk is that in fact like all of these different mirror symmetries fit together into like one gigantic 3-categorical structure. And like this will be like really something I'll just keep coming back to over and over and over. And it's probably like the most important thing that you could know about a 3D n equals 4 theory and why they're important. And then there's two other parts of this thing, two other kinds of relationships. So these things are just dimensional reductions. And so in math, these things like correspond to like decategorification. And like living up here, these are 4D n equals 2 theories. This is like where stuff from like low dimensional topology tends to live, like Donaldson theory and Seiberg-Witten theory. And the important thing to know here is that like the Donaldson Seiberg-Witten twist becomes like the 3D A model, like when you reduce. And then unfortunately, there's no B twist up here, and that's why this is not part of the mirror symmetry. Like it doesn't have a mirror symmetry. And then the other important ingredient is that like it's possible to take these 3D theories and reduce them to very special 2D n equals 2 comma 2 theories that have extra symmetry. So these things will have 8 supercharges instead of the normal 4. So this thing is going to be some way of getting 2D field theories out of our 3D field theories. And this is like where the mathematical theory, which is called like symplectic duality, lives. And this is like basically like where like my sort of interest like in this sort of stuff started, is that like I was living down here in like this part, this shadow of the mirror symmetry, you know, thinking about various interesting equivalences of categories, and we didn't know where they came from. And you know, eventually, like I met Matt Bollamore, Davide Gaiotto, and Tudor Demofte, and you know, they sort of explained to me that that they thought that like actually like the symplectic duality equivalence was really like coming from like this 3D mirror symmetry. Like it was really like some sort of a dimensional reduction or like a decategorification. And so then we started working together to basically like show that that was like actually true.
What is for you the statement of symplectic duality?
So for me, the statement of symplectic duality is that, I mean, I'll say it again in a minute, but for me, it's that there's like a certain Fukaya category of the, say the Higgs branch with like a particular superpotential and with like a B field, or like, you know, I'm going to use, and that thing is going to be equal to some kind of, take the B model on the Coulomb branch. So that's going to be some sort of coherent sheaves, also with a superpotential, and then deform it by like the Poisson bivector corresponding to the holomorphic symplectic form. And so that's going to give you some kind of like DQ modules, and that these things are the same. So for me, that's the statement of symplectic duality. So it's some equivalence between like a Fukaya category and a category of DQ modules or deformation quantization modules. These things are like very similar to Fukaya categories, and usually like this sort of an equivalence between this like analytic thing, which is kind of topological, something like a local system, and this thing that is more like a connection, like something more differential algebraic. Usually this sort of thing is called like a Riemann-Hilbert correspondence. And so basically there's a bunch of work on these kind of things by like Kontsevich and Soibelman, basically proving in general, when you have holomorphic symplectic varieties that you can, oh, I'm sorry. I got a little bit ahead of myself. Scratch that. That'll be when I have the same variety. So there's also another equivalence where actually I could have put the Higgs branch here, and I could have actually made everything be the same, it turns out. So I could have done the same DQ modules with the Coulomb branch and the same Fukaya category with the Coulomb branch, and like all 4 of these categories will actually be the same, and that's what I would call symplectic duality. So I'll explain like precisely like what I mean by this in a minute. I wasn't quite ready. But some place that this is going to come from is that when I do this like dimensional reduction, like on a cylinder, and if I do the dimensional reduction equivariantly for the rotation, like in an omega background, there's like this interesting thing that ends up happening, that the A and the B twists here go to A and B twists here, but there's actually like an extra deformation where you can add your rotation to the A model or add your rotation to the B model, and those 2 deformations both coincide. And that'll be kind of like the key thing to describing the symplectic duality. So this is like, you know, a lot. It's, you know, just sort of, it's like everything I know actually about this entire subject, like sort of like on like one board. But hopefully like by the time this is over, like this board will make sense. All right. So I want to start with sort of like my my favorite example of a 3D n equals 4 theory, which are like the abelian gauge theories. Or in math, people often call the Coulomb and Higgs branches that we'll see appearing in a minute, people call these things like hypertoric varieties. And these things are determined by basically like the following like set of data. So you have like an exact sequence of tori. And this thing is acting on the quaternions of dimension n. This is like a hyper-Kähler action, or a tri-Hamiltonian action. If you know what that means, it means it has a, this is a hyper-Kähler manifold. In particular, it has 3 different Kähler structures. And I want it to be Hamiltonian for all 3 symplectic forms. Like that. That's what this tri-Hamiltonian means. So there's like this data. This G here, this is going to be the gauge group. Can people like online actually see when I write in purple? Blue is worse. Well, good thing that that was the least important thing I wrote. So I was safe. This piece is going to be the gauge group of the theory, and then people call this the matter. And then it has like 2 other pieces of data, which will be very important. And so that's going to be, there is what's called like a real Fi parameter. And so that is going to be a character of the Lie algebra. So by that, so by a character of the Lie algebra, what I mean is some map from my Lie algebra to the trivial Lie algebra. That's a Lie algebra homomorphism. Or sorry, to the one-dimensional Lie algebra. That's a Lie algebra homomorphism. Of course, this thing is abelian, so actually this is like there's no Lie algebra structure here whatsoever, and this thing is just like something in the dual Lie algebra. But you know, if I had a non-abelian theory, like that would be some interesting condition. And then there's also a real mass, and so that is going to be a character of or an element of the Lie algebra of the flavor. And of course, this is only the right definition because this is also abelian. So this is, so this thing is a long exact sequence of tori. So this is an abelian group, that's an abelian group. And then there's also, like actually these things should fit into like triplets, but like I'm gonna set the other part of it to 0. So there's some extra stuff, but I'm gonna ignore that. All right. So this is like the data that goes into one of these abelian gauge theories. And then I told you that there's some sort of an operation on 3D gauge theories, which is called like 3D mirror symmetry. And this class is like especially nice because it's closed, like under that operation. So like if you want to like study things about 3D mirror symmetry, like this is the best class or first class to start with. And so the 3D mirror is like passed to the Langlands dual sequence. So that's going to like reverse the direction of this sequence, and then you keep the same matter representation. So this group I've trivialized, so like it's just going to get fixed by the Langlands duality, and then you just swap the T and the M. And then sometimes like you might need to put in a sign Like there's a couple of different conventions. I'm not going to be careful about it. All right. So then, like what I claim is that like out of this data, like one can actually get like some hyper-Kähler manifolds, and these things are called the hypertoric varieties. So the first one is called the Higgs branch, and by definition, it's just the hyper-Kähler reduction of the quaternions by my gauge group with this particular parameter. This has like a couple of like other descriptions. So like if I pick like a complex structure on this Hn to identify it with T star C to the n, which is I kind of actually already done implicitly when I started talking about like a real mass versus a complex mass, then the other way that one can think about this is as a, so this would give me a description as like a hyper-Kähler manifold, but one can also think of it like as a holomorphic symplectic manifold. And so in that case, you end up getting a complex moment map for your complexified G action. I just didn't. Yeah, I'm just not going to.
Is it important that you don't? But it sounds like it's important.
So for me, it's going to be important that I don't, because category O, which is the name of like these 4 categories that appeared here, that appears in symplectic duality, ends up being trivial when you turn on like a generic complex thing. So one does study that, studies turning on non-generic complex masses, and that's very interesting, but the generic ones are pretty boring. So that's why I'm not turning it on. Yeah, so this real, yeah, anyway, all right. So this is like a nice description, because this one is like purely in algebraic geometry. Just to be sure, do people know what I'm talking about when I talk about this moment map? Some people do, some people don't. So basically there is this definition of tri-Hamiltonian is that this thing has a nice map going to the dual Lie algebra tensored with the imaginary quaternions, which I'll call mu. And if I pick a complex structure on the quaternions, basically then this thing will split into real and complex parts. And then like that lets me write this thing down. And the other thing that will be important to notice about this is that this thing is actually going to be an open subset of the stack quotient of T star. So you can take the stack quotient of C to the n by G and then just take its cotangent bundle as a stack. This thing will be an open subset in there. So this is something that's like very nice. So this thing is actually just, you take the 0 level of the moment map, but then you just take the stack quotient by G. Like you don't impose like the GIT quotient. So for me, like this stack is like a very useful thing to have around. I kind of actually think of this thing as being like the gauge theory, and this thing as being like the limit when I think in my own mind. Okay, so there's this Higgs branch, and I'm going to give a better description of this thing in a minute. Most of what I'm going to do in this talk will rely on us having like a good description of this guy. And then there's also like the Coulomb branch, and that has like a very interesting description due to Braverman, Finkelberg, and Nakajima. Maybe I'll write it down really quickly, although I'm not going to use it at all, so I'm barely going to explain. Basically, what one can do is one can look at roughly the space of maps from this space, which I call, I write B for bubble, but one of my collaborators hates when I call it the bubble. So this map from this space that I'm going to call R into C to the n mod G I'll tell you in just a second. Yeah, so this space. Sorry? Yeah, you're right. Okay. So yeah, so I'm going to go back to calling it the bubble. Although so like my collaborators hate it that I call it the bubble. They think it should be the raviolo. So this space is basically the disk union with the disk over the punctured disk. And so here, like when I say disk, I mean like the formal disk in algebraic geometry, so spectrum of power series. And this is like a spectrum of Laurent series. And so like the picture that you should have in mind of this, and the reason why we call it like the raviolo is that it just kind of looks like you've got these like two disks, which is this one point that's got like some filling in the middle. And in physics, this filling is like a monopole operator. So anyway, so this BFN construction tells you that you take this space, you take this homology, it's actually a ring basically by smashing bubbles together, and you take its like spectrum. Okay, but I'm not going to use that at all. The better description is that you take the quaternions and then you mod out by the mirror gauge group with the mirror parameter. And the way that you find the mirror is you do Langland's duality of this entire sequence. And so this new gauge group, so that reverses the order. So at the Langland's dual of F becomes your new gauge group. So this thing is just another word for F Langland's dual. Yeah, in fact, maybe I won't even bother to introduce this other notation of the shrieks. So maybe I'll just say that you use M, and then you do this thing with respect to F Langland's dual. If I accidentally write a shriek, though, that's what I mean. Okay, so this is very nice because then I don't even need to understand what on earth Braverman, Finkelberg, and Nakajima were doing. I can just like be like, okay, well, I know about hyper-Kähler quotients, hooray. These are not the same. Oh, sorry. Yeah, these are the same. It's sort of, this is like basically the first, if you were learning about Coulomb branches, this is the first thing you would prove, is that these things are after you defined it, the first computation you would do would be the one that would prove that these things are the same. Oh, yeah, actually, you're right. Yeah, so they caught me. These things are not actually right because I didn't make my parameter be 0 here. So really, like this thing that I've written actually like resolves that Coulomb branch. So this thing was like the singular Coulomb branch. But for me, the Coulomb branch is actually going to be this guy. There's also a way of doing resolutions with the BFN construction, but since I'm not even using the BFN construction, I really don't want to explain how that works. All right. So let's actually okay, but this was all very crazy and abstract. Let me actually tell you how you actually use these things. All right. So the way that you actually deal with these things is the following. So they actually have a really pretty Lagrangian skeleton inside, and that skeleton you can actually just draw. So the way that you find the skeleton, I mean, there's lots of ways of doing it, but my favorite way of doing it is that if you take h to the n, or if I choose an algebraic structure, t star c to the n, this thing has its moment map for the d, complex moment map for the d action, which is like the full action. And that thing maps down to the Lie algebra of d tensored with c, which just ends up being, d is just, n copies of u1, so this thing is just c to the n. And if you actually write down what this map is, it actually just takes your coordinates like xi and yi, and then just sends them to the product. And so then if you take the 0 section of this moment map, there's a really pretty Lagrangian in here which is going to be which I'm gonna like study a lot, which I'm gonna call L universal. And this thing, as you can tell, it's gonna have a bunch of components, and the components are basically gonna come from just picking out of these n, for each of your n coordinates, does x vanish or does y vanish? So this thing basically like breaks into like a bunch of pieces, which are labeled by sign vectors or power sets or whatever. You know, for each n, you have, you know, a or b, and then some Lagrangian that's determined by that. So actually, let me go ahead and define like what this Lagrangian is. So my favorite model of the two-element set is plus and minus. And the way that I would write this thing down is that this thing is just xi equals 0. Oh, sorry, blue was the worst. Blue was the worst. So that you set all of the xi's equal to 0 whenever your alpha I is equal to a minus. And then you set all your yi's equal to 0 whenever alpha I is equal to a plus. And that determines for you some like Lagrangian subset. And sorry, and this is the universal. Sorry, yes, this thing is some gluing. Basically, depending on what I want to do, I like to, yeah, so this thing is not disjoint. Maybe like what I'm going to allow is I'm actually going to say that this thing, that was not a, so basically these things get glued together when you like actually go inside. Thank you. All right, so this is like my favorite like Lagrangian inside. And then, so why did I mention that? So now let me introduce like one other thing. I want to figure out, so when I take like this universal Lagrangian, this thing was in the 0 image of the moment map for D. So in particular, it's also in the 0 level for the moment map for G. So that's like some exercise that like one can do. So in fact, like all of these components actually survive into that, like into when I impose the 0 level of the moment map to make the Higgs branch. And then now, like I can just like quotient these things. And so my real L is going to be this L universal mod G. And then the, sorry. This will become like more clear in a minute. This is the thing that I would call L00 is going to be that L universal mod G. And then that thing is going to, yeah, be, again, this disjoint union of all of the L alphas, where these things are all going to be L alpha mod G, mod G's. Does that make sense? All I've done is just taken the quotient and then given it like some really like strange notation. And then I'm going to define like one other Lagrangian, which I'm going to call LT0, which is going to be just the intersection of L00 with this open subset. So basically, this did not depend on my moment map level in any way. So this thing is going to be some open subset inside of this guy. And this thing will actually be the disjoint, sorry, will actually admit a map from the disjoint union of a bunch of L alphas, but only certain ones will appear. And the ones that appear, I'm going to call stable. So this is the definition of stable. It's just like some of these components, when you intersect, you get 0.
So you have the upper
Oh, that was just a mistake. I should have written unif. That just didn't have the mod G in it. That's all that happened. I just modded out by G.
Here, when you do quotient, you don't have a T.
This is just stack quotient. So this thing is just some Lagrangian inside the stack, like the one with the 0, 0. Sorry, and then when I impose, and then when I like intersect it with this open subset, now I leave the stack and get into my honest hypertoric variety, but at a cost of I lost some of my components. So this thing had 2 to the n components, and this one has some smaller number of components. Like, and the ones that appear here are the stable, and then the ones that do not appear here I'll call unstable. Oh, T stable, sorry, T stable.
So your tuning function just records your choice of stability.
Yeah, exactly. T is just recording my choice of stability condition. It'll make sense why I'm using all this bizarre notation in a few minutes. Yeah. Yeah, the other way of saying it is, yeah, those things aren't in the T pre-image of that thing. But the way that I like it is that I just have this open subset, and like I just have less of these things. Actually, sorry, this actually probably wasn't the right thing to say. Actually, I should have actually written something slightly different. I should have actually said that this thing is this guy minus the unstable ones. Because I wanted to get an open subset. And the thing I wrote down was actually a closed subset. So sorry, that's the way I should have actually written it. So then the ones that are left over are the stables. But like basically like the thing that was wrong about what I wrote before is that like I sort of implied that if you had a stable component, you would actually have all of it, whereas actually you're going to only have some open subset of it. So that's the better way of writing this thing. Okay, so now, yeah, and actually, so then if I write it this way, then that's actually just an equality. Maybe that's the better equality, right? Okay. All right. Okay. Any questions about this? It's kind of weird. Okay, let me now like draw a picture of this. All right. So this combinatorics can be encoded in a picture. And the picture that I want to draw is actually just a hyperplane arrangement. Basically, you don't need to remember any of this because I'm going to draw for you a hyperplane arrangement. I'm going to draw for you a picture that tells you everything that you should have learned. All right, so basically the point is that there's a map from C to the n, which is equal to d dual to G dual. And inside of here, I have a favorite element, which is T. And I can take the pre-image of T. So this map is just like the dual of the differential of that map up there, which let me just give it a name. I just forgot to give that map a name. Let me call this map P for projection. This one will be I for inclusion. So I can take P inside of here. There's a particular subset, which is just P inverse of T, or actually really the inverse under the derivative. So this P is also inducing a map here. And this set is actually a torsor for F dual. Like if you pick any So if you pick any element in here, then you can take the difference between that element and your fixed element, and that'll give you some isomorphism with this F dual. All right, so the point is that we get that here on C to the n, we have a natural hyperplane arrangement. You have the coordinate hyperplane arrangement, right? Which is just like you have your coordinate hyperplanes in Cn. And then now I have this thing is just some like affine hyperplane living inside of Cn. And now you can just intersect your coordinate hyperplane with this other hyperplane, and that'll give you a hyperplane in F. And that is like the hyperplane arrangement I want to define. So this is going to be some hyperplane arrangement in F, and it's going to be defined by restricting the coordinate hyperplanes. Huh? Oh, maybe I should have made this be a real hyperplane arrangement. You're right, sorry. That's all right. Thank you. I mean, I could complexify it, but I don't want to. Thank you. So restricting the coordinate arrangement. Okay, so let's actually just like draw this. So like the example of like what I have in mind, right? It's like if you had just your coordinate hyperplane arrangement in two-dimensional space. You could take this pre-image and then say that my P is something like I just like sum the two coordinates. Then like you could take the pre-image of some like given element, and that'll give you some hyperplane that looks like this. And when you intersect your coordinate hyperplanes with this orange line, so this is like my F dual, basically I'm going to get some hyperplane arrangement in here. Does that make sense? Okay. So like so I told you that this hyperplane arrangement actually, and in fact, actually this is a little bit better than just a random hyperplane arrangement. This hyperplane arrangement is actually going to be what we call co-oriented, because like we actually know like what direction like positive is in R2. Like I know like what it means to be on like the positive side of this hyperplane and the positive side of this hyperplane. So in fact, like each one of these hyperplanes, there's actually a notion of what the positive side and the negative side is. And so that's what I mean by like a co-oriented hyperplane arrangement. So it's a little bit better than everything. It's actually like co-oriented. Okay, so why did I like tell you all of that? Okay. Well, the reason that I told you all of that is that now, like suppose I have a co-oriented hyperplane arrangement, like suppose I have this one. Then, and actually there's also like an order to the hyperplanes, like this is like my, my x1 coordinate, so that might be my first hyperplane, and this one might be my second. Just, give an order to the coordinates on Rn, that gives you an order to your hyperplanes. So now that gives me some sort of an order here. So and now, given this data, each sign vector alpha in this case 2 to the 3 determines a chamber. Which I'll call like delta alpha. And like, let me just show you the way this goes. So like, for example, so as I've said before, my favorite two-element set is plus minus for positive, negative. And so if I gave you plus, 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 that's telling you that I want to be on the positive side of all three of my hyperplanes. And so that like basically is telling me that I'm interested in like this chamber here. And then I could also say take, oh no, what's this guy? Does anybody know? It's plus minus minus. So this one's just plus minus minus. Okay, whatever. So you guys know what these things are. And then the theorem is that so I've told you that this space is just given by taking my original thing and then removing these unstable hyperplane arrangements. Let me say that this thing will be the union over the stable sign vectors of things that I'll call L alpha T. I guess I won't actually need that extra parameter, so I'll just call them L alpha T. So basically the issue is that like when I remove this, I might have removed some stuff from my original L alpha, right? Like I might have deleted some things. So the theorem is that like L alpha of T is the toric variety corresponding to the polytope delta alpha. In particular, something is unstable if and only if it just doesn't appear in this picture. And it's stable if it does appear in the picture. Does that make sense? All right, so this is like everything that that you'll need to know about hypertoric varieties. And now we're actually ready to get started, or like really get started. Okay, so I used about, what, an hour on that? 40 minutes? All right, so this is perfect. Okay, so now we're just gonna do stuff. And so I want to go ahead and okay, so first I'm going to tell you what symplectic duality was about, and then we're going to categorify it. And this is like a very weird approach on symplectic duality, I will say. This is like the, it's basically specifically designed so that I can categorify it later. It's like maybe not like the Platonic thing that you would read like in a, in a textbook. That's right. Well, when the textbook is written, I doubt they'll do it this way, is all I'm saying. Okay, so, and I'm only going to talk about symplectic duality for hypertoric varieties. Okay, so before, and what this is going to be is it's going to be some kind of an equivalence between two different kinds of sheaves that can appear like on my hypertoric variety. It's going to be like, it's going to be an equivalence of like a category of sheaves on like the Higgs branch and a different category of sheaves on the Coulomb branch. And I need to tell you like what kind of sheaves am I actually interested in. And so the first thing that I want to say is I actually was not quite done with my combinatorics. You might notice that I like never use this parameter m anywhere. And so symplectic duality is like not actually something that's about hypertoric varieties. It's going to be about hypertoric varieties plus a skeleton, plus a Lagrangian skeleton. And I've sort of already given you a Lagrangian skeleton for my hypertoric variety. It's this L T0 thing that I've written down before, but that skeleton is going to be too big. So I need to like tell you about a smaller skeleton, and it's going to work as follows. So let me go back to my picture really quickly. I think I need to work out. Let me do this. Sorry? I see, it's more balanced. I see, I should have known that, like that there would be a physics test. All right, so let's think about like what happens with this parameter m, which is no longer on the board. So this parameter m, if you remember, it was something that lived inside of the Lie algebra of F. Well, this hyperplane arrangement is taking place inside of the dual space of F. So this thing is taking place inside of like F dual. So that means that this thing is actually giving me like a linear functional. And if I have this linear functional, it makes sense for me to ask, does the function determined by m attain a maximum on my chamber or not? And so let me say that something is unbounded, something is bounded if it does. Or sorry, not theorem, definition. Alpha is bounded if M attains a maximum. Well, I also should have taken my T to be generic. Everything's generic. All right, so I take my random like M. Yeah, maybe let me just to be sure, I want to draw the one that's like 2, 1, 2. It's my favorite M. And then now like we can go back and we can look at like which of these chambers are actually bounded. Okay, so like obviously it doesn't attain a maximum on this chamber. Obviously it doesn't attain a maximum on this chamber or on this chamber. But it does attain a maximum on the compact chamber for sure. And then in fact, it also like attains a maximum on these non-compact chambers. Does that make sense? So these 3 guys would be my bounded guys. All right, so let me define my skeleton LTM to be just like the union of the LTs for alpha bounded. And of course, if this thing is like non-zero, in fact, also this thing will be stable. So I might as well just restrict to the stable ones. Okay, does that make sense? So this is going to be what I call like my skeleton. And it'll be important that I could have attained this from like my big skeleton, L T0, just by like removing some components. And those are like the unbounded components. All right, so this is like what we're going to try and do is I want to associate a category to this skeleton. And in fact, I'm going to associate 2 categories to the skeleton. And eventually, I'm going to associate two categories to the skeleton, but not right now. All right, so let me just say, and so before I do that, I need to just explain the difference between infinitesimal and wrapped sheaves. Or maybe I should say Lagrangians. Maybe the. All right, so basically I want to try and like associate some sort of category of constructible sheaves to this like Lagrangian skeleton, and there's like 2 options about like the way that I can sort of like make things behave. So the infinitesimal way that I can make things behave is that I only want to, so if I'm in Fukaya language, I want to only allow Lagrangians that are close to the skeleton. I'm not going to be very precise about what this means. So sort of the picture that I have in mind is like, you can't actually draw it in like this picture, but like if you had, like a cotangent bundle to like S1 or something, and S1 was my skeleton, I would only like want to allow Lagrangians that were like very close to this like S1 here. And like basically a more precise way of saying this is I want this thing to just be generated by the components of my skeleton. In some sense. And like if like like your like Fukaya category language, like in the case like if you were looking at like the cotangent bundle, like the so I was looking at like the infinitesimal Fukaya category, like of a cotangent bundle, say to something like compact. This thing is just, and my skeleton was actually just the 0 section. Although I think I'm going to use the notation where I just only write the skeleton here, and then you just have to remember that in fact that there was a T star X around. Then this thing would just be the same thing as just modules over the homology or over chains on X. And like basically like this is also like kind of what I would want the microsheaves to do. So this microsheaves is just going to be generated by like things that are local systems on the skeleton on the base. Sorry, this thing is supposed to be finite dimensional local systems. And these are all the same. Okay, so that's like one kind of sheaf. And then the other kind of sheaf that I want to talk about is like wrapped sheaves. And so these are basically like the exact opposite. So these things, if your skeleton here was like S1, these things would be generated basically by like the cotangent fiber. So this thing is generated by stuff transverse. So the generators are transverse to the skeleton. And then like what one can prove is that in this case, so this is a theorem of Abizayed, if you do like the wrap Fukaya category, and again, I'm only going to write the skeleton. You have to remember that there was a T star X around. I'm going to stop doing this after this particular board. Then this thing is actually just equal to all local systems of arbitrary rank on X. And that thing is actually isomorphism to modules over chains on the base loop space, assuming that X is connected. So like in this like particular example, like my loop space of S1 is the integers. And so this thing is like equivalent to coherent sheaves on C star. Because like this thing would just be the group algebra of Z, which is like Laurent polynomials. Okay, so this is like my first dichotomy, is like infinitesimal versus wrapped. And then my second dichotomy is going to be, this is the thing that's just like totally bizarre and that has never appeared in symplectic duality before, but I found that it made things much better.
In your theory, you also have an additional grading.
Does the original? So I am not going to get the additional grading. So I said that I'm going to categorify symplectic duality, and that's going to be a lie. And this is part of the reason why what I'm about to say appears. So unfortunately, I can only recover like the two periodization of symplectic duality. So like basically like so symplectic duality, you would like it to be an equivalence of categories, which I was going to say later. It won't actually be possible. One way of fixing it is you lift them both to Z, categories that have like an additional grading, and then you can like shear the grading and then make them match. And that's like what people normally do, or you can actually just forget the grading down to Z2 and then they'll match. So you can either fix it by like enhancing the categories or by making the categories less interesting.
I was going to ask you, I think you can enhance it, then the two categories that have them on the wrap will actually go. This is another really
Yes, that's right. I think that for the specific skeleton I'll write, they'll be the same anyway. But basically, I'm going to write down some intermediate things where I'm going to use some other skeleta where they will not be the same. So like for the category O skeleton, the infinitesimal and the wrap will be the same. But like, I wrote down like these skeleta like LT0. And so for LTM, they'll be the same. But for LT0, they're not. Or for L00, they're not.
X was a circle?
Yep. It doesn't matter. Okay, you're right, but this isn't going to matter because I'm not going to use either. Yeah, actually, you're right. I will fix that. Oh, here we go. Okay, I fixed it, and it'll be in orange so that people will remember forever that I was wrong. All right, so let's just do this. So then like this thing that's like pretty weird is that like also I want to like distinguish between like just like sheaves with just like ordinary homology. And then I'm actually gonna, as an intermediate, it is actually very nice to allow yourself to have K-theoretic microsheaves. So this is the thing that never has appeared, and like in fact it doesn't quite appear in our paper. Like basically it just would have been a bunch of work to actually make this precise when we could just like work with something a little bit more concrete. But let me just like roughly like tell you like the idea, and really I'm only interested in the infinitesimal versions. And so basically what I want to tell you is that there's a theorem which roughly says the following, that like if I have some base of like my symplectic manifold, and then I have like two guys like y1 and y2 that are mapping here, and let's say that both of these maps are proper. So both of my maps are proper, and then these guys are smooth. So y1 and y2 are smooth, and then x is proper. That basically the HOMs between, let me call these things pi1 and pi2, then the homology between the push forward of the constant sheaf on y1 and the push forward of the constant sheaf on y2, this thing is basically just given by the Borel-Moore homology of the fiber product. So this is like a very major computational tool that people use for computing like X between objects with sheaves. And basically the only thing you need to know about these K-theoretic sheaves, and the only thing that I actually use about them, is that you just do the exact same formula, so you're still allowed to push forward some objects basically from, and these things actually won't be arbitrary K-theory, that would be really hard. It's actually like complexified K-theory. So you can push forward like the complexified K-theory sheaf on both things. And then the only thing that changes is that now this thing just changes to like the Borel-Moore K-theory, or like the G-theory, if you want. Okay. And then you might think that this is like really, really dumb, because if these things were all spaces, there's a map between these things called the Chern character. And this is an isomorphism for spaces. And then you might ask, what else could you have other than a space? Well, it turns out that in the middle of my proofs, I'm actually I had my hypertoric variety as some open subset of a stack. And like for stacks, the Chern character is not an isomorphism. So like the simplest example is just that like the K-theory of just the simplest stack, which is like the quotient of a point by BC star, this thing is just like the representations of C star, which is just like the Laurent polynomial ring. And the homology of this guy is a ring in just a polynomial ring. And I'm just going to treat these things as being, this K-theory also is Z2 graded, so I'm just going to forget the grading here. So I just want to think of this homology as being Z2 graded. And basically the relationship between these two things is that there is a map from here to here, and it's basically this is called like the Atiyah-Siegel completion theorem. This thing is basically just like complete at the irrelevant ideal. So like there's like the relation for stacks, like this map will actually be non-trivial. And the point is that it's going to be super useful if I allow myself to have a stack. And this was something that we were the first ones, I think, to notice. And let me show you like why this is true.
Just make sure. What do you mean by KC and Y1? What kind of sheaf is that?
It's a sheaf of spectra. I know. But basically, I'm saying you don't even need to know, because basically all I'm going to do is I'm just going to say I have some favorite objects. They're given by these y's mapping down to x, and I'm just going to tell you that the HOMs are given by that. So basically you could try and do this like for real, but it wasn't worth it. So and I will say actually to be related to Mina's point, basically like there's some recent work of Eberhard, which sort of shows that like actually like when you're doing Z2 graded Koszul duality statements, you should actually expect like sheaves to get swapped with like, they call these things also K motives. That like basically like for like this Koszul duality naturally swapped sheaves and K motives. And then when you enhance them with the Hodge grading, then you can make it be like motivic sheaves get swapped with motivic sheaves. And like that's like where like that's where the bi-graded thing lives. And then there's like this Z2 graded shadow. But if you want to write down the Z2 graded shadow, you have to use these K motives. So like it's work of like some student of like or not student, postdoc of Straupel's, who's now a professor. Anyway. So sorry. So then you need to work with like actually like something like you need to work with motives. Like if you want to have the Hodge grading, that's like the lift of the Hodge grading. Then like it has a Betty realization to homology and like a K theoretic realization to these K motives, and like the duality that just lives on the motives, like swaps these two. These two realizations. And so when you pass the Z2 thing, that's why I'm getting this horrible equivalence. But like, let me show you why I did this. So the reason is now I want to look at just like the stupidest mirror symmetry of all. So it's like, why? Sorry, and actually let me tell you like what now my definition of symplectic duality. And then it's actually worked to show that this is actually the old one. This is just specifically designed to decategorify well. So my definition of symplectic duality is that like on the Higgs branch, I can look at like wrapped microsheaves. And then I can look at my Lagrangian LTM. And if I am on my other side, I can look at the same Lagrangian where now, right, the roles are swapped. So this is like on my Coulomb branch. So I guess I told you I would never write this again, but I guess now I am. So this thing is in like the dual Higgs branch, which is equal to the Coulomb branch. And then now I want to look at these K microsheaves, but the infinitesimally wrapped ones. And I claim that this is true for like any kind of parameters, like generic or not. And then when things are generic, basically what happens is that the wrapped becomes equal to the infinitesimal, and the K theory becomes equal to the not K theory. Well, okay, so I'm going to prove it for you in a second. Okay, so sorry, this was the statement that I want to prove. And okay, so it's a theorem. I mean, I'll prove it for you in a second. But basically, I'm just saying that this wasn't what people normally meant. But it is completely equivalent, because basically, like when you are in this totally generic situation, there's no K-sheaves anymore, like everything's just infinitesimally wrapped on the skeleton, and it's just like this Fukaya category is that Fukaya category.
So you don't want to think of the category of the entire difference, just this Lagrangian.
Yeah, right, because like basically like it's only about, the normal thing that people called symplectic duality is only about massive theories.
Sure.
And this Lagrangian, this is the way I'm encoding the mass.
Physics has a whole set of parameters there.
Yeah, absolutely.
You don't need to just, it's kind of a strange thing to do. I mean, sure, with the data you can construct a Lagrangian, but a much better statement will be just, something associated with the Higgs branch with this first parameter.
Yes, I mean, so that's what I'm saying, something associated with the Higgs branch, where my Higgs branch, I guess, depended on this T.
And so maybe this is,
yeah, this is,
it's one reflection of symplectic duality.
Yeah, okay, and so let me show you, yeah, and so let me show you why like this definition is like is easiest to prove. And the reason is that like if you look at the very simplest example, like you'll find that this K theory thing made everything way better than you had any right to expect, and it wasn't even hard to compute. It was like so easy to compute that like, you know, I mean, I'm going to be able to do it for you in like 1 second. Okay, so let's look at like my simplest example of like a symplectic duality, where I'm going to take one of my spaces to be and now I'm just going to start using always the holomorphic notation. So it'd be the quaternions, or if I choose this complex structure, T star C. And then my mirror is actually T star C mod C star. So this is going to be my, so these are the stacks. Both T and M are generic. Yeah, like I think it's like something like T is generic makes this true, M is generic makes that true. So this one, yeah, this one comes from T and this one comes from M. All right, but like you're gonna see like why this is like really nice right now. Okay, so now like what I wanna do, so here, my Lagrangian skeleton, just to remind you, it's just like these two components, it's just like the cross. Or if I were writing it in, so that's one way of drawing it. If I were drawing it in terms of these hyperplane arrangements, it's just this. Like, so I have, you know, a hyperplane arrangement with a single hyperplane. And then like basically this is a copy of C and that's a copy of C and they touch at a point. The other way of drawing it, right, is like inside of here I've got like my two axes touching. I think that's kind of like what I'm drawing here. Like that's this is just a, you know, this is a more realistic picture, but this is just like the toric picture. Okay, and then this one looked at my Lagrangian also. So this is what I was calling L00. And then the thing I was calling L shriek 00, this is the same thing, but just modded out by C star. As a stack. So basically like this, at this point, right, there's this stabilizer and it's like, got like a copy of BC star in it. So this thing's kind of big. Okay, and so now I want to prove this thing in like the very simplest case. So then like one can look at just like what are the perverse, what are like these perverse microsheaves or whatever. Yeah, I guess I should have also said that there was like a T structure. So you could actually think of these things as being like abelian categories. So I'd really like to look at like the perverse subcategory. So then it's just some statement about abelian categories. And so then this category of perverse sheaves on this guy, this thing has a very like easy like description. So this is like very old. So this thing is supposed to be like like wrapped. And so this thing is supposed to be generated by like two branes that are like transverse to each of these core components. And then when you compute their hums, like in fact, like they like wrap around one another. And like what one actually finds is that this category is actually the same as just quivers or representations of a quiver. Actually, sorry, people normally call these, I think, write these things as phi and psi, where you have a map U and V going in the other direction, or like 1 minus UV and 1 minus VU are both invertible. So that's like what, so that's like, this is some old computation. And now who did it is escaping me. So anyway, I apologize to those excellent. Do you happen to know? Yeah, maybe. I think it's like maybe like Granger and Mysonobe. I think who did it. And anyway, and then one can like just rewrite like being modules over this quiver as just being like modules over some algebra. And as a vector space, this algebra just basically looks like this. It just looks like a Laurent polynomial ring, or like a matrix that's just like a bunch of these. And then let me just say something else. I think this one's generated by U, and this one's generated by V. This X is, I think this guy. These guys are what I'm calling X. And then this thing's generated by like the identity of phi. This thing's generated by like the identity of psi. And maybe I got the U and V swapped or something, but whatever. Okay, so that's like a very like easy thing to write down. But then where have you seen this ring just 2 seconds ago? Yeah. It was the K-theory of C star. And that's also the K-theory of C mod C star. So like if one like goes like on this other side, and I was saying like you take these like infinitesimally wrapped K-theoretic sheaves on this, you know, on this brane L shriek. 0, 0. Well, I claim that this has exactly the same presentation because there's basically like because basically you're just going to take, I told you that when you're doing infinitesimal wrapping, things are just generated by the components. And so I have 2 components here. Each one is like, and I'm just looking at this scenario where I've just basically, I can rewrite this as basically I've got C mod C star. One of these components is actually the 0 section, and then the other object I have is actually 0 mod C star. And I can just start computing HOMs between these like 2 objects. And the point is that K-theory can't tell that there's a C here. It's just like that's just contractible. So then you just get this exact same ring. Just like as like the K-theory, you get this exact same matrix. And so these things just end up being like literally the same. Yeah. 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 So that's like really, anyway, but the point is like that's like really easy. Like if you set it up right. And then now the point is I'm just going to get everything else by just doing stop removal and like and micro localization to this like one and passing to open sets in this like one primitive example. And basically you can prove symplectic duality for like toric varieties in about like 3 seconds. And then what I'm going to do is I'm just going to tell you how I'm going to literally just categorify that strategy and prove it for 2 categories in about the same amount of time. And this thing goes, it's 2 hours, right? Okay, so I'm in good shape. Yeah.
So in the symplectic duality statement, in the generic case, does that mean we can simplify all those statements to like things about the Hayek category, or does that look like?
That's kind of what this, yeah, that's basically what this is kind of saying.
But is it like, what's the role of the Rozansky skeleton doing if you didn't have access to Hayek category?
I mean, to define a Fukaya category of a non-compact thing, you have to say something about like what you're going to allow like the brains to do at infinity, and the skeleton encodes that data. So it's not possible to just like, or it's not to just ask like, what's the Fukaya category of this non-compact manifold is an ill-form question. Like, so you have to give extra data, and this skeleton is the data. These are this is equivalent to stops at infinity. Basically, basically you could look at the contact boundary, and you would get like some Legendrians in the contact boundary, and you can rewrite all this in a more crazy form. So okay, so that's so the reason why this is very nice is when you set it up this way, like things just fall out in like a very easy way, and I think that like and this is kind of like a strategy sort of that Ben Webster used to prove symplectic duality for these hypertoric varieties in the first place, except for because like he didn't want to use these K sheaves, he had to like, this side looked really funny, and like he had to like, you know, complete with respect to the monodromy, and like it just didn't come out clean. And like this just sort of like, it's just the exact same strategy, but if you tweak the definition slightly, it just goes through cleanly. Of course, their thing they can tweak to do they can tweak it to get the bi-grading, and this one's a little harder to do that way because of the K theory. But like you shouldn't really be that surprised physically that this might be nice because like the B model isn't bi-graded anyway. So like if I'm going to get something out of the B model, like it's not surprising that it might factor through. Sorry, the 3D B model, like it might not be surprising that I can only get a graded Z2 graded statement. All right, so now let's like finish this thing off. So I'm almost done. So now, like basically from this, just by taking.
I'm sorry, for a moment I zoned out. I'm sorry, I missed the point, and I don't want to let you go on because I'm not going to follow anything else. Can you just run us through this example again?
Yeah. So okay, so the two examples that I have, so this is the a hyper and U1 with a hyper. And then like, and now like this skeleton is like the biggest skeleton that I'm can take sort of. And in this case, it's just gonna be the union of like the two coordinate axes, which like I could draw like that way. And then that picture is basically like living above this like toric picture. So if I want to think of it in hyperplanes, like that's like what I should think of. And then this one looks like exactly the same, although unfortunately this one's not as easy to draw with hyperplanes. When you have the stacks, they don't draw very well. But it's just the exact same Lagrangian, but mod C star. And when I say mod C star here, again, I'm treating this thing not as I'm treating this thing as a stack. So there's like a fixed point here under this like rotation, like it's rotating this way, and somehow that's going to make some contribution. So that's like the key thing to notice is that there's this, when I do this, there's this like contribution from the stabilizer, and that's going to be the whole point. And the way that I defined these K-theoretic infinitesimally wrapped sheaves was actually very simple. So this infinitesimal thing just means that the generators are just going to be the core components. And one of these core components is the zero section, and the other one is the cotangent fiber to zero. And so when you write things just in terms of the base, like not in terms of the fiber, the zero section goes to the zero section, and then the cotangent fiber just becomes the inclusion of zero. And now, like what I'm saying is if I have these two spaces, basically I can say that this category is just going to be the modules over the endomorphisms of these two guys. And the way that I said to define the morphisms of these two guys is I said take their fiber products and then take the K-theory. So one of them is going to be I just take the fiber product with this thing with itself over itself, this one with itself over itself. That's just this, and I take its K-theory. The other one, it's going to be the same. And like later on, I would want to know that this was actually a derived intersection, but right now that doesn't matter. So right now you can just think of that as being a zero. It doesn't really matter. And then these two guys, these things just give you 0 mod C star and 0 mod C star. And then there's just some like matrix product on them just coming from like convolving. And then what I was saying is that like if I had put homology here, which is the thing that happens when you don't have the K-theoretic sheaves, that would be wrong because this thing has like an x and an x inverse. This thing is the Ront polynomials, not just polynomials. And so basically by taking K-theory, I fixed it. And that was the whole point of this K-theory thing. So basically the point is that this thing swaps like the wrapping and the wrapping and the infinitesimal, and then it swaps the K-theory and the homology. Because like the homs in this one are you take these same fiber products, but just take homology instead. And so like that's like pretty wild. And there's like multiple ways that you could fix this. Like if I change this to be homology, then the way that I could fix this is by the Atiyah-Siegel theorem. It just tells me that I should complete to make everything have unipotent monodromy. So like basically like these guys, like the action of this X is the monodromy on my sheaves, like about when I wind around like this circle or that circle. And if I like ask that to be unipotent, then like that would make this thing match on homology on both sides, but I just chose not to. Not to do that. But when I go to this generic situation, the monodromy will become unipotent, and that's what makes everything the same. So I know that this is like a little weird, but it's not like really that bad. I mean, I just like had to compute K-theory of 4 spaces and remember this like old computation of Granger and Maisonneuve, and then like I have this like primitive statement. And now let me just go ahead and like finish this thing off. So like, how do I actually do this? So now I have So now by like taking products, I have this same thing if I just take like the product version of this Lagrangian. So let me now just say that I have T star C to the n, and then T star C to the n mod C star to the n. So this was the thing I was calling D before. So now like this is like my new mirror pair, and then I know that I have like this equivalence. So this is just by taking products of the equivalence I had before, nothing interesting. And then this guy has an action, like a residual action of a D on it. And really, if I was careful, this D is actually the Langland's dual of the other D. So this is just the, this thing is the n-dimensional copy of U1. And then one can ask, like, can I see this structure on this category? So in Telemann's ICM, this is actually like a weird way that I'm using his ICM. It's not exactly the way that appears in this picture. But in Telemann's ICM, he says that like if I have a D action on a variety, or like a group action on a variety, the way that I should think of that is that I should have an action of pi 1 of my, I mean, in general, I would say chains on the base loop space of my group. But of course, like this thing is a very stupid looking group. And this thing should map into the Hochschild cohomology of my category. Okay. Okay, but this actually like isn't such a complicated thing. Like normally to compute Hochschild cohomology, it's complicated, but this thing is actually just modules over some algebra. So let me call that algebra A1, because it was just one copy. And then this thing is just going to be some modules over some algebra, which I would just call AN, which is the tensor product of a bunch of copies of this category. And so then this Hochschild homology, in general, it might be very complicated, but in particular, it contains one part, which is just like the center of AN. And that's like actually exactly equal to this ring. So in fact, like basically the action of this D, according to Telemann, should just be interpreted like as the fact, like as just noticing that you have this inclusion of the polynomial ring into this center, and it's like, and it's this, and it is the, and in fact, there's really just, in fact, it's an isomorphism. So it's just like basically including your Laurent polynomials into each of these factors, or like into the diagonal factors. It's not very complicated. And then he says like one other thing. He says like, how should I compute like how I actually get the sheaves on the mirror? Or sorry, not sheaves on the mirror, sheaves on the quotient. So then he says the following. So now if I just want to know like what are micro sheaves on this Lagrangian mod G, like then I should be able to compute that from this other category by doing some operation. And the operation is, this thing is tensored over this big polynomial ring. And this thing has an inclusion of chains on pi 1 of G. And you should just take this tensor product. So all that means is that like every Hom space is a module here, and I'm just going to tensor it as a module with that. And like what this thing means, like if you like write this thing down, oh no, I'm sorry, I made a mistake. That should be over F. I'll explain why in a second. The reason being is that the chains on G are in the kernel of the chains on F. And so if you check like what this thing like actually does, it just like sets all the monodromies that are coming from G to 1. Like that's all this tensor product does. So that's like not like very complicated. And so anyway, so this is like an ansatz. And it turns out like this is true. Okay, so, but then the crazy thing is the following. So now I can look at what happened on the Langland's dual, or sorry, on the Langland's dual, on the 3D mirror side. And it turns out that what this does is it just unquotients this D to being just a quotient by F check. So like on the other side, like what this thing is naturally isomorphic to, sorry, I'm not explaining this super well. Shriek, although this thing used to be mod D, but then now I don't have any notation for this. I want to unquotient the G check action. And so this thing ends up being sheaves on my like universal guy, modulo F dual instead. And this thing is the 3D mirror. Sorry, that was really really poorly explained. What I'm trying to say is that this mirror, that like if you check very carefully like what this quotient does, maybe I can explain it this way. What I'm trying to tell you is that if you take the K-theory of BD, and then you tensor this thing, BD check, and then you tensor it with the over itself with the K-theory of F dual, or BF dual, this thing is just the K-theory of BF dual. I guess I'm just saying that like on the K-theory, this is just like doing an unquotienting. Like this quotient that's happening here just becomes like this formula in K-theory. And when you check that through, you find that it just unquotiented. And then we know that basically, and this thing would be the L00 for like the mirror to this. Sorry, okay. I'm saying that these two things are mirror, and like the proof of that passes through this, that this tensor unquotients. Let me try and say this like in a nicer way. So this picture actually comes from this 3D, 4D kind of relationship. The thing that I'm doing is I'm putting like my T star C to the N gauge theory on the boundary of a D gauge theory. And it turns out that when you take the S dual, it actually goes to the same thing. And then what I'm doing is that the thing that takes my D action, breaks it down to, forgets my D action down to a G action, and then quotients. So basically this is like some sort of like a partial Dirichlet, and this is like a Neumann. That thing is mirror to taking this D check action, quotienting by a Neumann for the F check. That will take you down to a G check and then a Dirichlet to forget about it. So what you get here when you follow this thing through is T star C to the N mod F check. And when you follow it through this way, you get T star C to the N modulo G, and those two things are supposed to be mirror, or 3D mirror to one another. And this thing is like just the one way of like implementing that strategy. This one is like in 3D reduced to 2D. So like I've really taken this whole thing and I've just like reduced it on a circle, but I'm just passing this computation through. But this is the computation I'm going to lift in a minute. So this is like kind of crazy. I don't know that this was the hardest part, in fact.
So this hasn't been, these Fourier categories have not been computed before in any way?
No, they have. Basically, the point is I'm trying to tell you this strategy because it's the strategy that like I want to lift. And basically, if you don't know the strategy that like I want to lift, like basically it just like won't make any sense what I'm doing. Basically, I'm telling you like a complicated strategy for computing these Fukaya categories that like basically will lift to the 3D picture. Yes.
It's what you're saying. So like you started with basically 3 hypers versus you one hyper.
Yeah.
You're saying you could just use, if you know how to gauge and stuff.
Yeah, if you just know that gauging gets swapped with ungauging under S duality, then like basically I'm just implementing that.
Right. And you just have to use this specific notion of gauge.
Yeah. So basically this mathematically is like what it means to gauge the 2DA model, like thanks to Telemann's ICM. And I'm saying if you track it through, what it does on the other side, it just ungauges this one. So this thing was like a D Langland's dual gauge theory, and then it became an F dual. So basically just ungauged it. And you might say like it's not possible to ungauge, and that's kind of right. It's because actually like mathematically this thing is really more about like the relative, like the thing I actually proved is actually something about the relative, this relative theory. I really knew this thing as a boundary condition. I did know you could think of that as being the free hyper mod U1, or you could think about it as some analog of the free hyper relative to U1 on the other side of. Anyway, it's a.
Well, that's kind of how the thing began.
Sure. Yeah. Okay. So now like I'm like 90% done. That was the hardest step. And in 3D that will also be the hardest step. Or actually, sorry, the hardest step is actually this first one. Sorry, the one I just erased, the step where you prove your first primitive equivalence. Okay, and now like I just need 2 things. So now we know this thing for any T star Cn mod.
Sorry, the equivalence is macro-sheet stuff with ordinary categories. Is this some standard stuff?
I think it's like GPS, but there is no ordinary Fukaya category for a stack. So like in the level of generality that I've set it, this is the only.
You really have to do it.
But I mean, maybe I'm wrong. Yeah, I mean, I think, but again, I'm not really doing that either. I'm just doing micro sheaves. But I'll tell you like the spot where you actually make contact with the Fukaya category. That'll happen in like 1 second. So we know now like this primitive equivalence where I know that my inside of here I have like my Lagrangian 0, 0. So remember this thing has 2 to the n components, and this thing also has 2 to the n components. And I know that my mu sheaves wrapped on this guy is my mu k sheaves infinitesimal on the other guy, and that these things are the same. That was what I just proved. And then now, like the thing that you want to do is now we need to like change my Lagrangians around. And so there's like 2 pieces that I needed to do. I needed to impose T, and I needed to impose M. I'm running a little short on time, so I'm just going to tell you how to do one of them, and then we can talk about the other one later. And the important thing is that it's going to swap. Like basically, when I impose T on this side, it'll impose M on the other side, as you might imagine. Like that's like what mirror symmetry is supposed to do to these parameters. And so this is just something you have to check. So let me say like precisely like what I mean. So I want to like describe this functor. The one, and I'm going to do the most interesting functor on this microsheaf side, the one that actually takes me from my stack to my variety. And on this side, it's going to be a more boring functor. I'm going to stay a stack, because I'm going to just leave my T alone. And then I'm just going to change my skeleton. Sorry, shrink. Or sorry, I guess I was just writing this with a T. So I put the T on the side. Sorry, this is my K sheaves infinitesimal. And then the point is that like you want to prove that this functor, that this commutes. All right, and so let me say, so the thing that's actually well understood is actually this side. Because people know like what happens when you remove Sorry, I guess actually in this case, neither side is well understood. But let me tell you one other thing that I needed to tell you about this equivalence that I wrote down in the beginning. So the thing that this thing does is, this equivalence says the following. So if you have like a chamber, like delta alpha, or like a toric variety associated to something, there's a nice object in here, which is like the projective, which is like transverse to this guy. Those are the generators of this category. By definition, I said this wrap guy was generated by the guys transverse to the skeleton. And then this guy actually has like some dual component. And I said it was actually just generated by the components. So this guy I would call like S shriek of alpha. And I should have pointed out that my primitive computation that I did at the very beginning swapped these two objects. I mean, I guess I implicitly did when I wrote down those two matrices, because like the entries of those matrices were the matrices with the Hams of these two guys. So this thing swaps this.
Sorry, what's the alpha to
It's the Lagrangian, the cocor. Yeah. And so I think of it as being like a, projective. It's the cocor to the Lagrangian, and then this guy is just literally the Lagrangian component on the other side. And those things get swapped. That's what Koszul duality is cocor swapping with components. Like they say it swaps like simples and projectives, and that's the geometric meaning. And what I want to claim is that I want to claim that this is actually like a quotient functor. So this thing, we wrote down is just modules over some algebra, which I was calling AN, and then I was tensoring it over these chains on D with chains on F. And then I was taking modules. And these projectives basically just correspond to like idempotents in this ring. Like this ring has like one idempotent for each of these projectives, and like taking the Hams is just putting this idempotent on either side. So the Ham from P alpha to P alpha. This is just like basic the way that the so let me call this algebra ANG. This is just basic way that you translate between a category and then modules over the endomorphism ring of a generator. So this is like, these idempotents sort of have this property. And like what I want to claim is I want to claim that this functor just kills all of the idempotents that are corresponding to unstable chambers. So that's in fact like what the theorem is that this thing kills all projectives corresponding to the unstable chambers. Okay, and so this is the part, so that part is actually, this is the thing that's actually hard when you want to try and like match this thing with a Fukaya category. So the issue being that it's very easy to see that there's a functor from here to here and all the P alphas get killed under it. Or all the P alphas corresponding to unstable chambers die. The thing that's difficult is to see that they generate. Because this thing, like by definition, is like given by like, taking some very obvious looking pre-sheaf of categories and then sheafifying it. And so when you want to pass to an open set, it's like not obvious that this is what what you get. And so this is a theorem that we had to like actually get help with. So this is a theorem that Benji and I proved with Laurent Cote. So that's like one hard theorem. But then once you know that fact, then you can just translate this thing over and you say that this thing just kills all the S alpha shrieks.
Just make sure, so your L of T0 is like a stack.
Yeah, so it's a stacky skeleton. And then I'm removing all of the, like a bunch of stacky pieces of it to get something that's just a manifold. And like basically the thing is that there isn't a good theorem about taking the micro sheaves and restricting to an open. There's a good theorem about what happens when you delete components from the skeleton due to GPS.
So this is like LT0 as an open subset?
It's an open subset. So this thing is an open subset in here. So this is restricting to an open. Sorry. Yeah. And like basically you have to prove a theorem. It's obvious that all these guys die, but it's just not obvious that that's everything. It's even obvious that that's all the things that die when you go to here. It's just not obvious that this is a surjection. So like basically once you prove this, then you know that this thing is just that thing modulo the p alphas. Does that make sense? And that's the hard thing you have to prove. And on the other side, that's just telling you that you just like kill the S alphas for the unbounded components. And that this thing is a surjection. So like that's like the theorem like you sort of have to prove. The fact that it kills the S alphas is like fine. And this is like what I would call, so this thing is like what I would call like restricting to an open or like micro restricting to an open. And this thing is like what I would call like stop removal, or the infinitesimal version of stop removal. And then the other theorem you have to prove basically goes the other way, that basically when you micro restrict here, it does stop removal there. So let me just draw you a picture of like what I'm doing. It's like what I'm saying, yeah, so I was gonna do my basic example. So like in this example where like I've got my two hyperplanes inside of T star C. But this one's actually not good because this one's like not really, well, it's not really a stack. Well, okay, yeah, but that's not the side that's interesting, right? I would never, there's no T for me to apply here. But you can still prove a theorem. This is not a case that would ever show up. You can still prove a theorem here. So what I'm saying is that here I could do something where like I could just pass to like say T star C star as like an open set. So this is like a very bizarre thing to do. This isn't something that actually shows up like in my thing. And so like inside of this T star C star, I would just have one of these components left, right? Well, sure, it would be punctured because my C star is punctured, yeah. And so you would know then what category this is. This thing is just local systems on C star. And like basically what I'm saying here is that this thing was just some like matrix algebra, which had like components like being C adjoint XX inverse. And all I'm saying to do is that you should just, I had two generators. I'm just saying now just restrict to just a single generator. And that just throws away all this part of the matrix. And that's indeed local systems on C star. Like that's what I'm trying to say. So basically I'm saying that like the operation of passing to this open subset was just throwing out a generator here. Yeah, I mean, I guess this thing has like a fully faithful left adjoint. So whichever, so that's a little bit, it's not quite like a reflection, but. Okay, but anyway, but this is like the operation that you have to do. So you have to prove in both directions that micro restriction to an open is removing a stop and vice versa. And then once you've like proved this theorem in like both directions, you can also sort of notice that it didn't matter like in what order you did this stuff. Like if you go to like T0 and then you want to go to MT, like I could have done this in either order. And you can also just sort of prove that like that all commutes. Like which direction you want to, whether you want to remove stops first and then pass to the open, or like whatever. But once you've proven these things, like that proves my theorem. Like it's basic because I'm just gonna like have to both remove a stop and micro restrict on both sides, and the operations just get swapped. Yeah.
And working equivariantly, you just keep track of some extra grading. And then gauging just means I just keep things in degree 0. So that's a simple operation.
So on the A side, that's not quite what gauging means.
Well, that's what it should be. That may, you know.
It means setting monodromies to 1, like the monodromies for the G action to 1. Because there's not quite a grading. But let me just say, again, this thing is way too complicated for hypertoric varieties. This strategy, sorry, this is basically the reason that I just went through this bizarre long thing is because I wanted to tell you how you prove things about 2 categories. And basically, if I didn't do this, at least here, all the operations I did were weird, but at least it was 1 categories that I was talking about. Whereas if I tried to do this starting with 2 categories, it just would have been completely crazy, right? Or it wouldn't have made any, I mean, it still didn't make any sense, but it would have made even less sense. Yeah, so now I'm going to tell you how to do this for 2 categories. Okay, so then it's how do you do this whole thing for 2 categories? And the paper where we do this has been done for weeks. We'll put it on the archive any day now. It's just we've just been procrastinating about maybe there's 2 or 3 remarks that aren't part of theorems that we're trying to decide what to say. But the paper should be, and I'll send it to anybody who asks. But you should really only have to wait a day or 2. It's so now I want to get 2 categories. Okay, and so now the first thing that I need to say is one of my sides was these wrapped microsheaves on my skeleton. And in particular, I just want to do this first for this, my favorite guy. And so now I have to tell you, and remember that this thing has this feeling that it is 2 vector spaces, phi and psi, with things going back and forth, such that 1 minus uv and 1 minus vu are both invertible. So this is my one primitive, this was my primitive guy. So now I want to categorify this. So I've given another talk here before, but let me just remind you. So the thing I want to do is I want to take these things to be what we'll call micro-local wrap sheaves of categories, whatever. So people also call these things perverse Schober's. They were studied by Kapranov and Czechman. And you do the same thing here. And what is this category defined to be? Well, this category had some a priori definition, and then one computed this quiver description. But this one has no definition other than by the quivers. So what people do is now I'm just going to upgrade phi and psi to be categories. So these guys were vector spaces. So now this thing is just going to be a category. And now u and v are going to be adjoint functors. And the reason that they need to be adjoint is that it's very difficult, that in order to categorify an equation between functors, you need a map between them. So the nice thing that being an adjoint means is that there's actually a map to vu and a map from uv to 1. So in this case, if I had been a little bit careful, if I do v first and then u, this thing would be 1 psi. I think the other one would be 1 phi. And so let's see if I did this right. So I do u first and then v, 1 phi, 1 psi. And then in order to make these differences, you can just take the cone. And I can ask for these things to be invertible. Ta-da! Not very hard. I said that this thing had an action basically of S1 on it. And that action of S1 was basically just corresponded to some map from the polynomial ring that basically, there was a map from the polynomial ring into this algebra I'd been calling A1 before, which is set like x goes to like 1 minus uv on one vertex and 1 minus vu on the other vertex. This was like my gauge action, like coming from this S1 action here. And basically, like you have the same thing here, so let me call these things.
Just remind me, when you say phi is a vector space, geometrically, what's this vector space?
Geometrically, this vector space is, so I've got some like random other Lagrangian, who knows what on earth it is. So I've got like my skeleton. I have some like random Lagrangian that's like in my space. And then basically one of the measurements is you test it against this cocore. And the other one is you test it against this other cocore.
So that's phi and psi.
These are phi and psi. These are called like nearby and like vanishing cycles. So these measurements are just testing against the cocores. So these things, so that's like what these things are, geometric.
So when you say associated phi category, what's that category?
It's sort of the same, so it's not I'm associating it. So this thing is the so this thing was, to describe this category, it's just all vector spaces like this. And I'm saying that this two categories just all pairs of categories like this. It's not I'm saying I lift every one. So basically you can go this way, but you can't go that way. And the map to go this way is like you could just apply like K0, right, to each of the categories, and then you would be there. So this thing is like not that bad, and this thing also has like an S1 action on like as like a 2 category, which is basically just given by like these guys.
So you're saying like each specify phi and psi as category is
An object.
An object in 2 categories.
Yes. And the HOMs are basically like, like a map of quivers. Like a map of quivers is like maps of vector spaces such that these things commute. It's going to be maps such that these functors commute.
So you have to do such data as the functors to such data.
Yeah. Yes. Yes. That's the HOM. Yeah, so that's like what this thing is. And then this thing has an S1 action, and this S1 action again is like is the manifestation of the fact that you can put this hypermultiplet on the boundary of 4D gauge theory. So that's like one side of my primitive equivalence. And then the other side of the primitive equivalence was the following. I had these mu sheaves, K-theoretic mu sheaves that are like on this same skeleton like mod C star. And now I need to tell you like how to lift those. And so if I remember, like that thing was the following matrix, right? I had my 0 mod C star mapping to C star, and I had C mod C star mapping to C star, and then I just took like all the fiber products. Now it's going to be important that I remember that like if I do this thing in the derived sense, I pick up like a shifted affine line. And then I just took like K theory of this whole big matrix. And then like now, like how could like one lift this? Well, like K theory has a pretty obvious lift. I could just take coherent sheaves. So instead, I'm just going to take coherent sheaves on C mod C star, coherent sheaves on this weird line, coherent sheaves on this 0 mod C star, coherent sheaves on this 0 mod C star. Ta-da, it forms a matrix via the same like convolutions that made that thing form a matrix. I'm just gonna look at module categories over that. And then like by definition, this thing just absolutely just decategorifies here. Let me say like one like very subtle fact. One subtle fact is I said that this was something about reducing in an omega background. And so I shouldn't have actually used K theory here. I should have used HP everywhere, but for these kind of stacks, I conjecture that those things are always the same, like the K theory and the HP. Basically, you can just prove that by hand in these examples, but you would want to prove this like in some more generality that we didn't do. Oh, I'm sorry, that should have just been infinitesimal. And the point is that these things are generated just by the things. And this is basically the KRS category. This is the KRS, the Kapustin, Rozansky, Saulina category, but just generated by these two objects. Like you could look at the KRS category for T star C mod C star, just with like generated by like the zero section and the cotangent fiber. And like that's like what this thing is. I don't even know anything about what it is wrapped normal when it's not categorified. That never appeared, you notice. Okay, and so then like the point is that it was like a pretty difficult theorem, but basically Benji and Aaron and I proved that these two things are the same. So theorem, there's like there's this, sorry, my primitive equivalence lifts. And that's like pretty surprising. It's not really very obvious that this thing has like knows about all the coherent sheaves on the line or something. And I should say that the structure that matches that S1 action is this thing has like a natural like central map from coherent sheaves on BC star. And so that's like basically the coherent. So this was the version of living on the boundary of 4D on the A side, and this is the version of living on 4D on the B side. So the theorem that we proved so our theorem was that our microlocal sheaves, wrapped sheaves of categories on, so this one was with myself, or Gamage, myself, and Maisel G. So we proved in the C star example that this thing is isomorphic to this other side. So this category of modules, I'm just going to call micro-coherent sheaves and infinitesimally wrapped of categories on the sky mod C star. And then that the S1 action here, so that makes this thing live in the 3 category of 2 categories with a topological S1 action. And this thing, there's like a 3-categorical Langlands duality, which again, I'm just talking about like how this thing lives with this bulk in the boundary, which exchanges this thing with 2 categories living over BC star. And this equivalence is there. And then the other thing we proved in this paper was that gauging gets swapped with ungaging. That this Langlands duality equivalence swaps gauging and ungaging. And so that gives it to you for all. So that thing gives you everything before you do restriction and micro-restriction. So this is like the version that I had when I had just killed those monodromies. And then the theorem that Benji and I just finished is that like restriction, we defined like what micro-restriction and stop removal meant. And showed that they were exchanged. It was actually extremely easy once you saw the stuff, like if you just copied what I showed you before, this is actually like very easy. So you get these wrapped microsheaves on an arbitrary Lagrangian, like get swapped with these micro on like the dual Lagrangian. T and M get swapped. And then what we showed is that like if you just decategorify by applying K-theory or HP, it's very obvious if you take K-theory, you have to work a little harder. If you do HP, which is what we really do, then this thing just becomes the equation that I told you before. Sorry, except for it becomes 2-graded. K-sheaves, infinitesimal, I'll shrink Tm, T, sorry, T. All right, so that's just true. I did want cat. I did have cat. Oh, no. Okay, anyway. So that's basically our 3D linear symmetry thing. Basically, it's just like very obvious once you set it all up right. Or sorry, it's very obvious minus this one theorem that we proved with Aaron. Like this theorem was really hard. This theorem is very easy once you know that theorem. Like in fact, like this paper sat around for like a year for no reason, essentially. Like we just didn't do it. All right, so I think probably everybody's exhausted.
No, that was great.
That's good. Good questions.
In your paper with David and Hilburn,
Uh-huh.
you had
Yeah, the first one. Uh-huh.
yes, you had there was a way of understanding extra result rating.
That's right. That's right, but I don't know how to get it out of the 2 category.
How to get a 2 category out of that?
Or no, sorry, how to get that Landau-Ginzburg model out of my 2 category. Like I have these 2 categories, and you might imagine there was some operation I could do to produce the 1 category, which is the bi-graded Landau-Ginzburg model, and I don't know how to do that. So I think that does not factor through that. I think that.
Actually, right, you should have said it that it was that in fact 2 Landau-Ginzburg models. There's one for the south. There's not just 1 Landau-Ginzburg. To
Sure.
write down the Landau-Ginzburg model, you basically.
Yeah, you have to choose a frame or yeah.
Yeah, but so there are 2.
Yes.
And there's.
Sorry, but I'm just saying for either 2 category, I don't know how to recover either Landau of the 2 Landau-Ginzburg models.
But you could ask whether that Landau-Ginzburg model has a 2 category associated with it, and it does, but it's.
Yeah, so I don't know. I mean, maybe like you have thought about these things more than I have, but I'm not sure that those things like factored through like the A twist and B twist in 3D. But then I don't know how to lift. Yeah. So basically, like I haven't found like a good. So I haven't figured out like for example, like say starting with like the HT twist or something, some good way of getting that Landau-Ginzburg.
Well, we know, right?
Oh, maybe you know. Okay.
Well, when you're comparing your 1 category.
Yes.
You reduce the problem to some endomorphism algebra, and you say, well, no, okay, the one on the left is the same as the one on the right has victory. Okay?
Yeah.
So what we can do is we know how to, from both Landau-Ginzburg models, produce those algebras.
Right.
Just to solve it, because we know how to solve Landau-Ginzburg model.
Right.
Now, when you say there's the obvious, it's not obvious, is, well, there are several things which are not obvious in that language, which is, okay, so maybe, let me just stop.
Okay. Yeah, but basically.
More of a, maybe,
yeah, but basically what I'm saying is that I don't know how to relate that picture to this picture. Like that's the answer. And that like that picture I think like needs to actually come from like the HT twist and.
Yeah, I mean it sort of has to do with just there's more than one way to get a limit to a 2D A or B model.
Yeah, exactly.
So